Algebra I Honors, Lesson 4.3 Relations and 4.4 Equations as Relations. So we start to get into the power of mathematics, the ability to take data and put it into recognizable form, and to do things with it, to look at it, to analyze it. So there's 4 ways to represent a relation. A relation is just a set of ordered pairs, like these right here. It's 5 pairs, and we can do it as ordered pairs. There we go. Table, which is going to be here. Graph, which is going to be here. Or mapping, which is at the bottom. And we'll come and get all that done as we go along. So let's do it as a table. Well, it's insane as it seems. It's just if you put in 3, you get out 2. Put in -1, you get out 4. Relation and a function, which is coming soon, is just a machine where I put in an x and I get out a y. Important to understand that. We call the x value the independent value and the y value the dependent value, because we get to pick whatever x we want. Hey, let's see what happens when we put 3 in. That's independent. Oh, what do we get out? Oh, it depends on the 3. It turns out we get a 2 out. So that's just the way it works. And then, of course, we can use it as points, which if I have letters, I use letters. If I don't, I use ordered pairs. Why graph, you might say? It's really not helping me. Well, you never know. You can see patterns in the graph that you might not see otherwise. And finally, mapping, which is a little tricky because I don't quite have enough space to see everything. So a 3 maps to a 2. This is what I meant by a function machine. I put in -1 and I get out 4. Put in 0, I get out -3. Put in -3, I get out 4. Put in -2, I get out -2. And then finally, how do we determine domain and range? Well, this is pure memorization. The domain is the x values, the range is the y values. So domain, and I've abbreviated, make one of these funky brackets, and we say 3, -1, 0. Wait a minute. We should really write those from little to big. Do we have to? No. Is it a good habit? Yes. Will there be math teachers in your future say it's got to be in that order? Yeah. So you might as well do it now. Problem is we lose their matching. You don't show that, -3 goes with -3. No, it doesn't. So that's a little bit annoying, but it's not the end of the world. Do I have to write 4 twice? No. So that's how we handle relations. Just, ways to look at data. That's all it is. So in 1990, New York purchased 12,000 acres for protection of bald eagles. I lived in New York in 1990. I don't remember this. The table shows the number of eagles observed in New York during the annual Midwinter Bald Eagle Survey. That sounds like a real fun time. From 1993 to 2000. So they went up, obviously. Bald eagles are making a big comeback in the United States because the DDT is gone, and apparently that helps the eggs. Anyway, determine the domain. Well, we pick a year. So we're going to go from 1993, and I want to say all the way up to 2000. Now, it is discrete values, so I could just write them all in. But I'd rather write it differently. So since it's the x value, I'll do this. X, and then we make this vertical line. It means such that 1993 is less than or equal to x is less than or equal to 2000. Do not get hung up on the notation. You could have listed 1993 all the way up through 2000. That would have been fine. The range, which I'm going to have to put over here because I foolishly did not leave myself much space, is also given in discrete values, but I'm just going to do the same thing. I'm going to say the range. Actually, I should put a R here. Notice I can't make my little brackets worth a darn unless I focus on it. This is domain. This is called set notation, by the way. Y such that 102 is less than or equal to y is less than or equal to 350. Could have listed them all out. Works either way. but I'm a fan. I like right now. My little set notation makes me all warm and fuzzy all over. Graph them. Tricky. We got 7 years here. I'm just going to keep it in the upper right corner. I'm going to make this 1993, 4, 5, 6. I'll label it every now and then. So if somebody comes along, 7, 8, 9, 2000, they could actually say, oh, I know what he did. He won every year. And then here I'll make this, we have to go up to 350. There's 10 boxes. I want to go from 100. So that's 400 minus 100 is 300. Divided by 10 is about 30 each. So we'll call this 130, 160, 190, and then I'm not going to label anymore just because it's getting way too annoying. But it will count it. 190, 220, 250, 280. I'm going to label one here just because I'll lose track otherwise. 310, 340, 350, 380. So notice there's no rhyme or reason. You could do this a dozen different ways. It's just the way I decided to do it. So in 1993, I had 102, about there. 116 in 94, about there. 144. Notice I'm ballparking it. I'm not trying to be perfect. Just trying to get a rough idea of what this looks like. Sounds to me like from 96 to 97, they screwed up their measurements. Same thing in 1998. Or they get rid of a predator or something. 244 is about here, and then 350 is about here. Immediately people say, oh, I got to fit a line in there. No, nobody said anything about fitting a line. Nobody. They just graph your points. If you're going to do it my way where it's not discrete, yeah, you probably should fit a line. You should fit it in because it's, theoretically following that curve. And then, of course, this is what I said about data. What's going on? And, more birds. I'm a person of few words. It just means that, it's going up. They're growing in population. What's an inverse of a relation? Well, that's an extremely complicated subject, so we make it simple. We just say flip the x's and the y's. And what we're saying is, can I actually make a relation where I count the number of birds and say, oh, this must be the year 1997. So we flip our independent-dependent concept. Hey, it's year, I don't know what year it is, but I modeled this data. And there are 752 birds. Oh, it must be 2010. Oh, it must be 2012. We could actually go backwards. So just a little bit more practice. Express the relations as a set of ordered pairs. So it would be, don't need my squiggles now. 2, negative 4, 3, negative 4, 5, negative 8, and 6, negative 7. Inverse would be flipping them. Again, why would we do that? Well, like I said, we can turn some data on its head and make some interesting assumptions. Negative 4, 2, negative 4, 3, 5, negative 8, 5, and negative 7, 6. And that's it for relations. And we talk about equations as relations. When equations have two variables, what's the solution look like? I have a y and an x. We very, very typically write this as a y equals. And I am sure most of you have seen this. We like to write it as y equals mx plus b, because we can represent many things, not everything, this is linear. I'll just say often as the multiple of some number plus some number. So find the solution set for y equals 2x plus 3 given the replacement set. So I put in negative 2, negative 1. I say y equals 2 times negative 2 plus 3 equals negative 1. That's true. Now we're just seeing if the points fit. Negative 1, 3, y equals 2 times negative 1 plus 3. We get negative 2 plus 3 is 1. That's false. 0, comma 4, y equals 2 times 0 plus 3 is also false. Last but not least, 3, comma 9, y equals 2 times 3 plus 3 equals 9. That's true. Just more practice. Now, what we will do more often is being given a domain and then go find out what we have. So we're saying negative 3, negative 1, 0, 2, 4, and add 5. Negative 3 plus 5 is 2, 4, 5, 7, 9. B is 8 plus 5, so it's the same thing. Just teaching you how to use the whole y equals mx plus b thing. And the ordered pair would be negative 3, comma 2, negative 1, comma 4, 0, comma 5, 2, comma 7, 4, comma 9. So, get used to knocking data around. It's what you do in math and science and business. You got to do all this. Now we're building you all the way up. 4x plus 2y equals 10. Well, we already know how to solve an equation for a variable. Better had anyway. So we're building you up to graphing. Plug in negative 1, the classic middle school technique, make a table. X, Y, negative 1, 0, 2, 4. Negative 1 times negative 2 is 2 plus 5 is 7. 0 gets me 5. 2 gets me 1. 4 gets me negative 3. Negative 1. Notice I'm not labeling anything because I'm just using each tick mark. Now we notice this very interesting thing. We get a straight line. That's why I've been calling it linear and things like that. So we will typically throw a line through it. This may not be perfect, but you get the idea. That's it. Solving a solution set. We used this domain, and I assumed it was continuous, not discrete. Discrete means just set spots. So I graphed a line. If not, I should just graph the points. Make sure you understand the difference. Don't just blindly do things. Know what you do and why you do it. Oh, that's it. And that was quick. So, fair amount to cover there. Get cranking on it, and good luck and happy mathing.